Okay, so kind of revisit where we left off, and then I'll introduce kind of a new idea, a little more linked probably to that Learn Smart you should have kind of already done. We were talking about this example where we're looking at the 1936 election. This literary digest tried to send out these 10 million mailers and predict the election, but they got it very wrong. So we left off kind of talking about one of the main reasons was they over-selected wealthier individuals, and so their sample was made up more of Republicans kind of than the the general population. So that was our selection bias. They over-selected using this method that using a car and telephone registration. But we said the same problem would exist if when they sent these 10 million mailers out that 5 million to Republicans, 5 million to Democrats, so we eliminate the selection bias. If 2.5 million Republicans responded but 0 Democrats, we have the same problem, right? Now we have a whole bunch of Republicans in our sample, and it doesn't match up with the breakdown of the population. So when this paper went back and found people who voted in the election, they also did this thing, like they tried to get at how likely the people were to respond to surveys or mailers. And what they found was that for every single category, it didn't matter what the Literary Digest did, however they got their names, whether it was they own neither a car or telephone, they owned both or only one, in every single one of those groups, the people who voted for Landon in that election were just more likely to respond to any survey, right? So notice no matter what category we look at, the Landon response rate was higher than that of Roosevelt. So we had a non-response bias. For whatever reason, people that voted for Roosevelt are just less likely to respond to these mailers, right? So we not only had a selection bias, we also had this non-response bias. And that's really why the Literary Digest poll got it so wrong, right? Now, what are some other things that could have went wrong? Well, people lie to you, right? Either maliciously or non-maliciously. So people might have said they were going to vote for Landon and then ended up switching and voting for Roosevelt, right? They non-maliciously lied, right? They were telling you the truth at the time, but it ended up not being what they actually did. Right? People might maliciously lie. Well, in the context of that example, I mean, I don't know why you would lie about, to some random company about who you're voting for, but you might. Maybe you don't want to, admit you're voting for one candidate. But in general practice, we see a lot of this going on when you try to elicit like responses for people's drug use or kind of any illegal activity, right? There's a lot of malicious lying there, right? They're just going to give you a wrong answer because they don't want you to know the real one. Also, there's been a lot of research recently about just kind of the phrasing of questions. So I think the one I had to leave last class was, if I was asking a survey question of, I don't know, 30% of the American public smokes at any one point in their life. We just want to know, how many packs on average do you smoke this week? Right? Kind of phrasing it is, trying to make the person feel comfortable, right? 30% of the population smokes, so we're just, how much do you do smoke a week? Whereas if I started out that question saying, cancer kills X number of, or lung cancer kills X number of people every year, we could directly link it to smoking, and so we want to know how often do you smoke each week, or how many packs do you? Well, okay. You set the question up very negatively, you're much more likely to get that person to respond with probably like maybe giving you kind of a lowball kind of estimate about how much they smoke, whereas before they might have been more comfortable to tell you the actual number, right? So just the phrasing of the question, but also phrasing of the question, if you phrase it in a way that's confusing, that also can cause problems, right? So think of an example like this where, let's say I had everybody that's in the class, let's say I had them in front of me, we're all together, and I asked every single person and recorded it, what your health was today from 1 to 4, right? Well, a lot of times when I do this, because I do this with the iClickers usually, when we're not in this hybrid environment, and sometimes you'll see some 4s in there, right? And I always get a little bit concerned about those people, and more often than not, at least one of them says, I don't know, I am a 4. I was out till 3 a.m. last night or whatever. But so a lot of the times it's, I thought 4 was the highest, right? Because there's kind of a poorly phrased question. It really, from 1 to 4, well, it makes me think 4 is the best, right? Whereas if I look closely, no, 4 is the poorest, 1 is kind of being in the best health or feeling like you're in the best health. Right? So it might be misunderstanding of the question. What's a selection bias that could exist? If I'm asking everybody in this class about their health, and I want to make statements about the population as a whole in the US, what selection bias might I have? All of you are pretty much the same age, right? You're all in a much lower age bracket than the average American, right? So hopefully that your health, right, reported health is going to be much better than the population, which includes 80-year-olds, right? So we have a selection bias, maybe a non-response bias here. Who might be more or less likely to respond to a question like this? If you think about people, or think about the health of the people, if I'm thinking about people who feel relatively healthy versus those who don't, who might be more likely to not respond to this survey? Yeah, probably, if I had to guess, probably people who don't feel as healthy. They may not, want to share that information or embarrassed or whatever. Whereas I can't think of a lot of reasons why someone who feels healthy wouldn't want to respond, right? Why do they care? So maybe we have a non-response bias built in there as well. One thing I haven't talked to you about this point, but we did say people non-maliciously lie. Well, what if I felt like a 1.5? Well, I have to either answer 1 or 2 here. So I'm essentially like, when I make it discrete, I've kind of forced people to lie to me, right? If I feel like I'm in between those two, I can tell you a 1 or 2, but that's not really accurate, right? I'm non-maliciously lying to you either way because I actually feel like a 1.5. Right? So sometimes even in the way we set the answers or the responses up, if we don't leave them open-ended, we can kind of force people to really not, there's going to be a little bit of error, right? A little margin of error there. And like I said, this isn't a survey design class. So if you take I'm sure there's a marketing class that's more similar to this, but like survey designs would start to, I'm kind of bringing up some of these things just to point, I want to highlight that there could be biases that exist in a survey, class you would, survey design class, you would start to go into, okay, how can we eliminate all of these, right? How can I not make it a subjective sounding question? I want to strip it of any emotion. I want to make sure that I'm selecting the right proportion of people, but that's not where we're going to go. I'm just kind of bringing up some of these that we're aware of these bias exists. Right? Another good example is always how many alcoholic drinks do you have on average each week? So if I ask this to kind of a general kind of class that I have, what's my selection bias? Pretty easy, same as before. I've over-selected college kids. I mean, if I'm comparing that to the general population, you guys have slightly different drinking habits, right, than the general population as a whole. So, that was my selection bias. Non-response bias, well, maybe I get a lot of no responses, but I get a lot of zeros. Maybe if anybody is concerned if I was collecting this on iClickers of me looking at it and you're not 21, maybe you just go with 0, right? And that's one of those examples where anytime we have any type of behavior that's not even necessarily legal but socially frowned upon, we want to make sure that we keep these surveys and these questions anonymous as possible, right? Because if you can ensure anonymity, we see responses that are a lot different than when you have a survey where the respondents feel like, maybe my name is being linked to all this information. Right? So selection, non-response bias there. People might lie to you, right? Underreport their drinking. They might over-report it. There's always one person at the party, that wants to tell you they can drink the most. And then also, right, you might non-maliciously lie. If you don't keep track or you don't keep a log and you're like, I think it's around 5 or 6, so I guess I'll just go with 1.5 or 1 to 5, right? Well, who knows? If I look at the actual amount that person drank, maybe they were supposed to be in this category, but you're doing this from memory, right? So, this might be causing some people to non-maliciously lie to you as well. So, kind of talked about kind of all these. I just want a general discussion. I think we'll revisit this Trump elected bias on Friday, just so we get every day this week a little bit of discussion of this bias and kind of hearing it on more days, maybe kind of some of it will stick a little bit more. So we'll return to this and kind of have this example. I'll post a paper on Canvas and then bring it to class on Friday that kind of goes through maybe some of the biases that exist in all the polling for the 2016 election, right, where the polls were very, very wrong. So we'll talk about maybe why there, okay? But I want to make sure we have plenty of time to get through talking about sample mean distributions today, So what am I thinking about when I'm thinking about the distribution of sample means? So if I had some variable x, right, and it starts out, it's normally distributed. Excuse me, I'll think about kind of income, right? And the average income in the U.S., I was looking it up before class, it said it was it 51,000? It might have been the median. Let me see. I had it pulled up somewhere. Yeah, I mean, this is not real exact, but I'm guessing it's around there. So let's say the average, income in the U.S. is $50,000. We'll just say that, okay? Just so we have a number to work with. If I select any one person at random, what's the probability that they make, I don't know, $150,000? Well, it's pretty far from the mean, but doesn't seem that unlikely, right? That we know there are people that make that much money. So if I select one person at random, the probability they make $150,000 seems pretty reasonable. Well, what if I selected 100 people at random? What's the probability that on average they make $150,000 across all 100 of them? Well, that's a lot less likely, right? I mean, that would mean that I'd have to have a lot of people in my sample, and it wasn't really distributed the same as my population, because I know that the average of my population is 50,000. So if the average over these 100 people is 150,000, I must have had some like multimillionaires in there or something, right? So if I'm looking at sample means, I can already start to think about, oh, okay, well, there's going to be some values that aren't very likely for me to see. If the true mean is 50,000, my sample over 100 people, I could very easily see, 53,000 as my sample mean. That seems a likely outcome. 47,000 maybe as my sample mean. But to see 150,000, that seems very unlikely across 100 people. So we have certain values that are kind of more or less likely than others. And what's going to end up being true is that if I took, say, 1,000 different samples, all of a size 100. So I take one sample size 100, I calculate kind of the sample mean income. I take another sample of 100 people, calculate their sample mean income. I do that 1,000 times. Well, if I had these 1,000 different sample means in Excel, I could create a histogram pretty easily, right? And I could calculate the mean of those sample means and the variance of those 1,000 sample means. So what ends up being true is the distribution for that sample mean, right? Those 1,000 different sample means will depend on the sample size I take. And this is the idea that, okay, well, what if I, sampled 2 people? What's the probability that they have an average income of 150,000? Well, not real likely, but it's possible. It's a lot more possible than seeing 150,000 be the sample mean for 100 people, right? So as I take samples of different sizes, that's going to impact the distribution of these sample means, okay? So what's going to end up being true is if I take a sample of size lowercase n, right, that the mean of my sample means, so I took 1,000 of these different samples and I wrote down the sample mean for each one of them, the mean of those sample means will be the population mean from the original data I sampled from. And the variance of my sample means will be the original variance of the data I sampled from divided by my sample size. Okay? So just trust me for right now. I'm going to prove to you this with data today, but for now, just assume that this is true. Okay? So if that's true, switch over the dot cam here. Second to catch up. All right, there we go. So what we're thinking about is I have this original variable x. It's normally distributed. Here's its population mean, and it has some population variance. If I take samples of size 100, the mean of my sample means will be the original mean of the data I sampled from, right? So here's my distribution of sample means. Here's my distribution of the original data, right? The original variable x. So this could be income, and this is kind of mean income over what I said, I think it was 100 people. And then we have the variance of my sample means will be just the original variance divided by my sample size, okay? So just believe me, that's true for now, and I'll prove it to you with some data here in a second. Okay? So this is kind of our general setup. Knowing something about the distribution of the original variable x, we could determine some things about the distribution of our sample means, x bar. So, another thing I want to kind of point out, and I'll just go over 1 and 2 in a second, but if I want the standard deviation, right, that's just going to be the square root of the variance, right? Well, if I know my variance of my sample means is equal to the variance of the original data I sampled from divided by n, then my standard deviation is just the square root of that. But I can write that a little bit differently because the square root of anything squared is just itself, right? So I could rewrite this as the standard deviation of the original data divided by the square root of n. So these two things are the exact same thing mathematically, just written a little bit differently. Oh, thank you. Still, I don't know if I'm ever going to get used to that. There we go. So sorry, what I was saying was here we've got the variance of my sample means. If I want to get the standard deviation, I just take the square root of that, right? But I can rewrite this a little bit differently because the square root of anything squared is just itself, right? So these two things are exactly the same mathematically, just written a little bit differently. Now, points 1 and 2 here, if the original, the variable I'm sampling from, if that variance goes up, well, then the variance of my sample means goes up as well, right? If I'm looking at a variable of height that has a much lower variance than the variable of income, well, then my sample mean incomes are going to have a higher variance than my sample mean heights, right? So the original variance of the data kind of influences the variance of my sample means. But then as I take higher sample sizes, so if n goes up here, if my denominator gets larger, what happens to the entire fraction? Well, if the denominator goes up, then this goes down. So higher sample sizes actually decrease my sample variance. I'll go over this a little bit more here in just a second. And this is something that we should never have to check in this class, but we do want to make sure if we have a really large sample, it can't be too large relative to our population. There's almost no examples. I mean, the populations are so large that we're dealing with, we don't really ever have to worry about this. So let's put some actual numbers to it. And then I'll kind of revisit this idea of having a higher sample size. So let's say I have every birth in Indiana in 2004. I have this data set. I can calculate the mean and I can calculate the variance. Right? So if I sample 36 babies, right, from this population, what would the mean of those sample means be of size 36, and what would the standard deviation be? Okay. So what's this going to look like visually? So we're going to start out, we have this variable x, which is what, birth weight. We're told that the mean is 3,287, and the variance was, I think, 360,000. So when I'm thinking about the distribution of my sample means, when my sample sizes are, what, 36? Well, the distribution of my sample means should be centered around that same value, that population mean. Okay? So it should be centered around the same value as the variable that I was sampling from, but that the variance of my sample means, right, will be the original variance divided by my sample size, so 360,000 divided by 36, or 10,000. And then I think I wanted the standard deviation, so that's just going to be square root of the variance, square root of 10,000 here. I get 100. Okay. So knowing that information about the original variable I was sampling from allowed me to kind of determine the mean and the standard deviation for that distribution of my sample means. Okay. Any questions on this before we keep moving? Okay, now it switched. So, I could go through, calculate that. Sure enough, I get 100 as my standard deviation, and 3,287 will be the mean of my sample means. What if I have the same setup, but I now sample 100 babies? Well, if the standard deviation for the distribution of my sample means of size 36, sample size 36, was 100, when I take samples of size 100, you look at this equation, what's going to happen to my variance? So if this goes from 36 to 100, my new variance or my new standard deviation should be lower than it was before, right? Because if the denominator goes up, the entire fraction gets smaller. Right? So I know if I go from 36 babies, where the standard deviation was 100, when I have a sample size of 100, my standard deviation should be even lower, right? Something lower than 100. So the only answers here that meet that criteria are the ones that have a standard deviation of 60. Now, regardless of my sample size, the mean of my sample means is always the original population mean of the data I sampled from. So I know that my answer is going to have to be C. Right? Now, I could go ahead and basically just do this exact same thing again, right? The mean of my sample means isn't going to change, but now my sample size instead of 36, I would just put in 100 here, right? And resolve it. But it's basically the same procedure. But because I know that when I take higher sample sizes, right, it's going to drive up this denominator, which would then drive down my variance. Okay. Any questions on that? Shouldn't be too bad. So I'll try to use another example as I'm describing these kind of slides. So I've mentioned a little bit, but that if we take higher sample sizes, so n goes up, my variance goes down. Right? So why is this the case? So if I think about, and don't read this title, I don't like this example. So think about the original variable x we're looking at is, actually, scratch that. I'm going to do my own. I'm trying to think about this. So let's say I've got this variable, which is height. I know height is normally distributed. And I start to think about, I don't know, maybe the average height, I think it's something like, if we look across men and women, we'll say that it's, I think it's like 60, maybe 67 inches. So if the average height is 67 inches, about 5'7", right? We know that it's pretty likely if I select one person at random, they're, what's the probability that instead of, 5'7", they're, 5'10" or 5'5" or, 6'1" even. We know that those are all relatively not very unlikely things for us to see for any one person. In fact, we could even see any one person be like 7 feet tall, maybe 4'9", right? Whatever kind of extreme heights you want to choose. But if I then look at a distribution where I'm looking at my sample means, and let's say I took samples of size 10. All right. Well, now let's say this was 7 feet tall, so what? 12 times 7, so 70, so 84. Right? Or we're going to kind of think about being 7 feet tall. Well, what's the probability that I see over 10 people, the average height or the sample mean for 10 people be 7 feet tall? Not near as likely. In fact, all these higher values aren't as likely as before. Same kind of idea with all these extremely low values aren't as likely for me to see if I'm looking at the sample mean of 10 people. And so I try to kind of draw this to highlight this, but I didn't do the greatest job. You can kind of notice I try to draw this distribution being a little bit more of a tight distribution, right? A little bit more peaked, like the tails have kind of tapered off. And so, maybe I should have drawn it a little bit more kind of peaked like that, where I'm trying to get at the variance of my sample means. Because I'm going from size 1, you can almost think about the original variable is like if the sample size was 1, right? We're just looking at one individual. If I go to a higher sample size, that's going to drive down my variance, which will peak my distribution, right? So it's going to kind of draw that in. And if I go to, samples of size 100 or something, Well, now these values are all like very unlikely. Only values kind of near that mean are going to be the ones that I see. And the values that are further from the mean become very, very unlikely. Right? So this is good for me because if I can't see the population mean, when I take higher and higher sample sizes, I'm greatly increasing the probability that the sample mean, if I'm only able to see one sample mean, the probability I see that one sample mean be somewhere near the population mean just went up a lot if I can get my sample size to be higher. Right? And that was kind of the idea here. If we go from the original variable to a sample size 5 to 50, our distribution just keeps getting more peaked. And then the probability of seeing values around that true population mean, if I'm only able to take one sample, well, then they've gone up, right? So now I feel more comfortable looking at the value that I see from my sample and making inferences about the population. And it kind of makes sense, right? Just the more observations I have, the more information I have about the population, right? So I should be able to get a more accurate idea about where that population mean is. You have another picture here where it just highlights like when n is 1, right? I kind of started this out, it's like a uniform distribution. It's not a perfect square because there's sampling here. It's not like I have an infinite number of samples, but when the sample size is 1, we could have a very, very high variance, right? So that values further from the mean are still pretty likely. But once I get to a really high sample size like 50, notice the probability of seeing values far from the mean is essentially 0. And then seeing something that's in between 10 below and 10 above the mean, that's where we start to see those probabilities actually are relatively high. That I see something that's really close to that mean of 50. Right? When I had the sample size that was as high as 50, right? As opposed to sample sizes of like 1 and 3. So the higher the sample size, the lower the variance, which kind of gives us this more peaked distribution. So I've kind of been setting these examples up and talking about this in a way such that if the original variable is normally distributed, then I was drawing the sample means as also being normally distributed, right? That's what I did right here. I was drawing kind of normal distributions, right? But what happens if, oops, the original variable, let's say it was uniformly distributed? Well, what ends up being true is even if the original variable is uniformly distributed, the sample means will be normally distributed if we have a sample size over 30, right? So this is just called the central limit theorem. It's kind of a proof. You can show that as long as I have a sample size over 30, the distribution of my sample means will approximately be a normal distribution. Doesn't matter what the original variable I'm sampling from starts out as. And as we get higher and higher sample sizes, it just becomes more and more of a close approximation. Okay? So I have a kind of visual here, just to kind of get at this. If we started out with 4 different variables, none of these are normally distributed, right? If I then take samples of size 2 and I look at the distributions of those sample means, well, these are definitely not normal yet. But once I get to samples of size 6, a couple of these already start to look like a normal distribution, maybe a little bit of skew to some of them. But then by the time I get to 30, right, that central limit theorem is met, and each one of these distributions of my sample means is normally distributed. Okay? So we could walk through the mathematical proof, but I think it's always easier and all more convincing to me, honestly, if I see things in data. Right? So let's say I had this huge data set, population data, every birth in Indiana in 2004. Right? So I've got about 88,000 births. I've got the recorded birth weight, gestation period, so length of the pregnancy, this health measure, which is an APGAR score. It's a health test for the child. And then the maternal smoking information. So 1 if the mother smoked while pregnant, 0 if not. Okay? So with this population data, I had it in Excel. It's very easy to calculate the mean of each one of these variables and the standard deviation, right? I mean, I think it'd be pretty easy for you guys to do that, right? Just equals average equals STDV dot P, because we're dealing with population data. And I get the mean and the standard deviation for each one of these variables, right? So kind of interesting to look at this. The one that's the most interesting, I mean, I guess it's sad, but, right, if this is a 1 if the mother smokes while pregnant, so 18% of mothers smoked at some point during the pregnancy. in Indiana in 2004. Hopefully maybe this is better now. But yeah, I think that's a little bit higher than you would expect. But if we wanted then to look at not just the mean and the standard deviation, but let's look at the distribution of these variables. So birth weight, one of these biological things, sure enough, once again, we get kind of this nice normal distribution, right? This is almost a perfect normal distribution. Now, the length of the pregnancy or gestation weeks here has quite a bit of a left skew to it. This is the idea that we can see premature births. We don't see children born at like 11 and 12 months, right? So we kind of have this long left tail. Same kind of thing with that health score. First of all, this is not even a continuous variable. This is discrete, right? And it kind of has this weird, maybe a longer kind of left tail. So it doesn't matter if the original variable isn't continuous. When I start to calculate sample means, I could see 8.321, right? So my sample means are still continuous, right? And that's all I need, okay? I didn't draw the graph, but for maternal smoking, right, it would be one bar at 0 that was what, 0.82 high, and then the bar at 1, which was they smoked, would have been at 0.18. So that wasn't very interesting, so I didn't graph it, right? So that variable of maternal smoking, this variable of the APGAR score, the length of the pregnancy, these are all definitely not starting out as normally distributed variables, but birth weight was, right? So what should be true, right, is if I sample from these variables, right? So I'm going to randomly sample 100 babies, right? I'm going to then calculate from the sample of 100 births, the sample mean birth weight over those 100, the sample kind of gestation weeks for those 100 births, the sample mean for tobacco use, and the sample mean for the APGAR score over those 100 births. I'm then going to do that 1,000 different times. So I will then have stored in a separate Excel file 1,000 different random samples of size 100 and the sample mean calculated for each one of these 4 variables. So once I have these 1,000 sample means in this other Excel file now, well, now I can calculate the mean of those sample means, just equals average, and select them. I can calculate the standard deviation of those sample means, right? Pretty easy to do in Excel. And what should be true, if what I was telling you earlier is in fact true, was, right, the mean of my sample mean should be the original mean of the data I sampled from. Well, I already have those calculated, so I can check that. And that the variance of my sample mean should be the original variance divided by n. Or if I go back to that other form, the equation somewhere here, it could just be the original standard deviation divided by the square root of n. Well, if I take samples of size 100, the square root of n here would be, square root of 100 is 10. So all these standard deviations I had, the standard deviations of my sample mean should just be these divided by 10, or move the decimal point one place to the left. Okay. So, oh, here we go. Oh yeah, so standard deviation divided by 10, right? That's square root of 100, square root of the sample size. So sure enough, I did these 1,000 different random samples. I then calculated the mean of those 1,000 different sample means. Notice, I mean, they're a little off here, and in fact, most of this is just due to rounding. They're even closer than what it looks like. But notice the mean of my sample means is always just the mean of the original variable. And the one reason why they're a little off, theoretically, if I actually looked at the actual math proof instead of just proving to myself with data, I need to be looking at all the sample means, so an infinite number. I can't practically do that. I could do something like maybe do 10,000, and there I would get an even closer approximation. But even with 1,000 samples, we can kind of see the sample mean of my, the mean of my sample means is just whatever the original mean was from the data I sampled from. Okay? Any questions on that? It's not too bad, I don't think. Now the standard deviation should be the original standard deviation divided by 10, which sure enough, once again, with some rounding error, the rounding makes these look a little bit further than they actually are. But all of these are the original standard deviation divided by the square root of 100 or divided by 10. Okay. So kind of, this is like, I didn't just put these numbers here. I actually ran these random samples. In fact, I don't think I have something in Excel for this until we get to confidence intervals, which I don't think will be maybe next week, but for sure the week after. where I can show you how you can create these random samples. I won't expect you guys to do it, but yeah, these are actual kind of random samples I took, and what I was saying plays out in the data exactly. Right? So not only did we say that was true earlier, but we said no matter what the variable starts out as, I showed you that little picture earlier, once you get to a sample of size 30, the sample means should be normally distributed, right? Some of our variables didn't start out as normally distributed, but the sample means should be, right? So here's the sample means for birth weights. I mean, this is a perfect normal distribution. You know, if we compare this to the original variable, so I'm going to go back up here for a second. If we looked at the original histogram for just the variable of birth weight, we could see births that were like premature, like down at like 800 grams and as high as, you know, kind of in the 5,000s. Well, when I take samples of size 100, I no longer have the variance of the original variable. I have the variance divided by my sample size. So my variance should go down, right? The denominator gets larger. And I shouldn't be seeing values far from that mean as much. So sure enough, when I go to the sample mean distribution for birth weight, notice now I don't see any values below 3,000, right? And that's the idea that, yeah, if I select any one birth, I might see a premature birth that's like at 800 or 1,000 grams. But over 100 births, to see the average birth weight be 1,000 means I have pretty much 100 births randomly that were all premature, right? So unless, you know, the rate of premature birth goes way, way up, that makes no sense. And sure enough, the distribution of our sample means is a much tighter distribution, right? The range only goes from like 3,000 to 3,500, as opposed to what before it was like all like 0 all the way up to like 5,000, 6,000, right? But it's a normal distribution. Well, what about the variable of kind of gestation or the length of the pregnancy? That didn't start out normally distributed, but when I look at the sample means, notice there's a pretty nice normal distribution, right? And I can see values, right? The range of values I see is much smaller, right? 39 to 37, whereas if I look at the original variable, I could see weeks of the pregnancy as low as 25, as high as kind of 47 there. So looking at the sample mean distribution should just have a much lower variance or just be a much tighter distribution, right? The range of values I see has went down quite a bit. And then the APGAR score, we get a nice normal distribution. And even on that maternal smoking variable, which was just a 1-0, we'll get kind of this nice normal distribution here, okay? Any questions on this? So here's our normal distributions. Okay. All right, so I think I want to try to get through one example here. So here, oh, excuse me. Cut that from the video. So I've got the different steps. And it's going to be, we're going to kind of return now. We've talked about sampling. We're going to return to some of the ideas that we had talked about with just looking at standard normally distributed variables, right? Or normally distributed variables. So if we know that our sample means are going to have a normal distribution, as long as we have a sample size over 30, well, I can turn any normal distribution into a standard normal distribution, right? So what we were doing before was, I don't know, let's say we had some variable x, it was normally distributed, we knew the mean, we knew the variance. We could turn any one x value into a z-score by subtracting the mean and dividing by the standard deviation. Then once we had that z-score, we could look that z-score up and find the area to the left. Right? Well, as long as we take samples over size 30, the distribution of our sample means will be normally distributed. We'll know that the mean of our sample means is the original population mean of the data, and the variance will be the original variance over the sample size, or the standard deviation would just be, right, the square root of that, okay? So if I'm thinking about here, well, okay, if I know all this information, what's the probability that I see this value for my sample mean or anything below it? Well, I have a normal distribution. I can very easily turn this into a z-score, However, now instead of looking at some value for x, I'm looking at some value for the sample mean. And now I'm subtracting the mean of my sample means and dividing by the standard deviation of my sample means, which if I write this out, right, the mean of my sample means is always just whatever the mean of the original data I sampled from was. And the standard deviation, we have an equation right here for it, so I could plug that in. So it's going to look a little bit different, but really the setup for this z-score was the exact same thing as what we were doing before, just subtracting the mean and divided by the standard deviation. It's just now, instead of subtracting the mean and the standard deviation of the original variable we're looking at, now because we're looking at cutoff values for the sample means, I have to use the mean and the standard deviation of my sample means. Right? But other than that, it's the same procedure. Once I have the z-score, I can go to the table, look that value up, find the area to the left of it. Maybe that last step, sometimes we have to do some transformation. So if I wanted the probability that it's greater than, well, then once I look that value up in the table, I have to subtract it from 1, right? There might be some additional steps there. But really, the procedure is exactly the same as what we were doing before. It's just that because the standard deviation of our sample means is a little bit more complicated, right? It has an actual formula now. The z-score is going to look a little bit different than when we're just looking at kind of the not looking at sample means, just looking at the variable itself. Okay. Any questions on any of that? All right, so let's look at some actual values. We'll kind of end on this. I didn't get to this on the other section, but I think it'll be better if we can end on this, so we have a little extra time. So let's say I've got some variable x. It's normally distributed. It's got a mean of 5 and a variance of 2,500. We take a sample of size 100. What's the probability that the sample mean I see is somewhere between 10 and 15? Okay. So what's the setup going to look like here? We have this original variable x. It has a mean of 5 and a variance of, I think it was 2,500. Right? So I know the distribution of my sample means will be centered around that same mean of 5, right? But the variance, right, of my sample means is going to be the original variance divided by that sample size of 100. So this is what? 25. Which, to make it a little bit easier, my standard deviation would be square root of that, or a standard deviation of, a standard deviation of 5. All right. The question then asks, okay, what's the probability I'm in between 10 and 15? Right. Well, I can turn this normal distribution, I can turn these values into z-scores. Okay. How do I do that? Well, the z-score equation we have for the sample means, I'll take that cutoff value I'm interested in, 10. I'll subtract the mean of my sample means, which was 5, and divide by the standard deviation of my sample means, which was also 5. So I get a z-score of 1 here. And that kind of makes sense because once I calculate the standard deviation, 10 is 5 away from the mean, so it should be 1 standard deviation away. I could then do the same thing. I'll plug 15 in here. 15 minus 5 divided by 5 is 2. All right. And once we get to this stage, it's the exact same thing that we were doing before. I can look up that z-score of 1. It's gonna give me kind of this area. I can look up that z-score of 2. It's going to give me this area. If I subtract that kind of smaller area from the larger one, I'm left with just what's in between those two values. So once I have those z-scores, did I close it? I did. Got a lot of things I need to close. I don't think I dragged it over yet. Sorry about that. I thought I had that pulled up. Oh, jeez. Come on. Rotate. Zoom in. All right. There we go. Okay. I have to do an update. Let's see if we can actually get this to work. I don't want to sign in here. All right. Well, we can look up the Z table online. This is kind of nice, right? So let's go to Google. Let's do standard normal distribution table. I don't know why my PDF isn't working, so hopefully I can pull this up somewhere. All right, so we could look up these different Z values. I look up one, it's like 0.8413, 0.99 or 9772 if I look up that Z score of 2. Right? So this area, 0.8413, this green area, 0.9772. And in fact, now I subtract the smaller one from the larger one. This should look exactly like an example we did, I think on, maybe on Friday, I don't know, last week, maybe on either Friday or this Monday even. Right, once I get to that Z score, it's the same thing as what we were doing before. Right, just look them up in the table, find those two areas, and that last step, sometimes I have a little bit of transformation to do. I have to subtract the smaller area from the larger area. Okay. Next class, we'll work through some more examples. I'll make sure I get my Adobe updated, I guess. But really, it's going to start looking very similar to things that we've already looked at. So, you know, I can find the probability of being above certain values. It's just getting used to using this new Z-score. And then we'll also introduce the idea of sample proportions, okay? So I'll probably add in a few more slides. We got through a little bit more. So on Friday, I'll kind of update this file. So if you've already downloaded the lecture slides or something, make sure before Friday's class you kind of re-download them. I'm going to add a couple more slides in there that we'll be covering, okay? All right, I'll get an online quiz up today as well. That'll be due before we start class on Friday. Other than that, you just got that Connect assignment right now. So I would suggest, you know, try to start working on that, getting through as much of it as you possibly can, and get me questions early on it. Okay? All right, I will see you guys on Friday.